Welcome back to Honors Calculus. In this video, we're going to be looking at the product and quotient rules. These rules will give us the tools we need to evaluate the derivative of the product of two functions and the quotient of two functions. Very on-the-nose kinds of names here. All right. Without further ado, let me get my head out of the way and let's dive right in. I'm going to call this a theorem. We're going to state it and then prove it. We need two functions, f and g. Again, sometimes I'll see this written using u of x and v of x, which is perfectly valid, and we'll do some work with that later on, but I think f of x and g of x are a little bit easier to follow. And I claim that the derivative of the product f of x times g of x is f prime of x times g of x plus f of x times g prime of x. And in order to prove that, we're going to use some limits. That should be a surprise. We know that f and g are differentiable, which means that f prime of x is the limit as delta x goes to 0 of f of x plus delta x minus f of x all over delta x, and g prime of x is the limit as delta x goes to 0 of g of x plus delta x minus g of x all over delta x. And the derivative of f of x times g of x, which I'm going to write as f times g evaluated at x, because I think that seeing that setup will make it a little bit more obvious how this limit is being set up in the first place, and then we'll expand it out in not too distant future. We're taking the limit as delta x goes to 0 of the product f times g evaluated at x plus delta x minus that same product f times g evaluated at x all over delta x. And yeah, the product f times g is f of this argument times g of this argument. So this is the limit as delta x goes to 0 of f of x plus delta x times g of x plus delta x minus f of x times g of x all over delta x. And then in our next step, we will use mathematicians' favorite trick, inventing something that wasn't there. I'm going to actually slide this all the way over to the left side of the screen because this is going to be a very long line. I am going to invent something that was not there. I am going to just randomly subtract f of x times g of x plus delta x. Now, I can't just arbitrarily subtract something, but if I immediately add it back in, then I haven't really done anything at all, have I? I've taken something that looked not too bad, I've made it look very messy, but I haven't changed the value in any way, shape, or form. Whoops, sorry about that. I am too close to the edge and I'm hitting my scroll bar. Told you that was a long line. And then it gets worse because I have to break this up. I'm going to take the first two terms and the last two terms and write it as two separate fractions. And I'm going to do my best to write this small enough that it will actually fit on the screen. And then I'm going to notice that in the first fraction, I've got g of x plus delta x appearing in a couple of different places. In the second fraction, I've got f of x appearing in a couple of different places. I'm going to factor those things out. And then I'm going to use properties of limits. Limit of a sum is the sum of the limits. Limit of a product is the product of the limits. And this is separately. Once again, I hope I can fit this all on the screen. But I've got the limit as delta x goes to 0 of the first part times the limit as delta x goes to 0 of g of x plus delta x. And then f of x is actually doesn't have a delta x at all, so I can just leave that alone. And the limit as delta x goes to 0 of that last bit. And of course, the first limit is exactly the definition of f prime. The second limit, as delta x goes to 0, g of x plus delta x is g of x plus 0, which is just g of x. Then I have f of x, and then I have exactly the limit that is the derivative g prime of x. I got there, right where I said I was going to get. It's messy, it's tedious, but it works, and now we know the rule, and we don't have to follow the whole process each time. We can just use the rule. So if I need to evaluate the derivative of 3x times the sine of x, my first function here is 3x. My second function here is sine of x. So I want the derivative of 3x, which is 3, times the second function, which is sine of x, plus the first function left alone, 3x, times the derivative of sine of x, which is cosine of x. Once I know the rule, I can follow the rule and everything will work out and I don't have to think about it anymore. This can get messy when you have more complicated things going on. We can have the product rule sitting here and also need the chain rule at the same time. X squared times the sine of the square root of x. Right? We have two things being multiplied together. We've got x squared. We've got sine of the square root of x. So we want the derivative of the first thing. The derivative of x squared is 2x, and then the second function is left alone, sine of the square root of x. Then we want the first function left alone, the derivative of the second function. The derivative of sine is cosine. But because the argument is a function, we have to use the chain rule and multiply by the derivative of the square root. Which, again, I've used that. It's 1 over 2 square root of x. If you don't know it offhand, it's not that difficult to figure out. But if we can save ourselves a little bit of writing, then why not? All right, simplifying things a little bit, we've got a 1/2. We've got x squared divided by the square root of x. There's a couple of different ways you can write it. Since everything else is involving square roots, I'm just going to call it x times the square root of x. All right, that's x squared over root x simplified. And that makes it look a little bit happier. All right, so that lets us handle products. I said today was the product rule and the quotient rule. So I guess let's look at some functions f and g, which are differentiable and have the property that g of x is non-zero. And the quotient rule is a mouthful. The derivative of f of x over g of x, I claim, is f prime of x times g of x minus f of x times g prime of x, all over g of x squared. You'll notice that the stuff in the numerator looks fairly similar to the product rule that we've dealt with previously. That's actually not a coincidence. We could prove this using the limit properties, and it would work. It would look very similar to the proof that we've already done for the product rule. But the whole point of all these rules is so that we don't have to go back to the limit definition if we can avoid it. And we can avoid it. I claim that f of x over g of x is the same thing as f of x times g of x to the negative first power. All right, this is the composition of two functions, which means that taking its derivative is going to be a little bit messy, but this is the exact same function that we're trying to take a derivative on. But now it's written to look like a product. So we're going to get f of x times g of x to the negative first, right? Derivative of first times the second, plus the first one gets left alone, times the derivative of the second. All right, we've got a power rule going on, so it's going to be -1 times the same argument raised to the -1 minus 1, which is -2, and then multiplied by the derivative of the argument inside. The derivative of g of x is g prime of x. If I clean up a little bit using properties of exponents, this is f prime of x over g of x minus f of x times g prime of x over g of x squared. I can find some common denominators by taking that first fraction and multiplying top and bottom by g of x. and then I can combine across in the numerator. To get the quotient rule that I said I was going to get. So for example, if I want to take the derivative of sine of x over x squared, following the quotient rule, I need the derivative of the numerator. Derivative of sine is cosine. I need the denominator left alone, minus the numerator left alone times the derivative of the denominator. The derivative of x squared is 2x, all over the denominator squared. Clean up a little bit. Notice that there's a common factor of x in this case, so we can reduce a little bit. And we've got it. All right, so I would like you to try this one, the derivative of sine of x over cosine of x. Of course, you know your trig identities well enough to know that sine x over cosine x is tangent of x. So I'm really asking you to find one last trigonometric derivative rule so that we can complete our set of trig derivatives. But take a couple of minutes, see what you can do with this problem, and I'll see you in the next video.